So this is,
I have a question about homework that's due on Monday, the third one. So are we gonna have to do lesson 5 and lesson 6 problems for homework for the third homework? I saw it on the
so in general,
mhm.
we have 2 classes a week. We have 2 lessons a week. And you turn in your homework just once a week, and it's always for the 2 lessons of the previous week. So this week, if we did lessons 5 and 6, then the homework for Monday is lessons 5 and 6.
Thank you so much.
And that's always the way it is. That doesn't change. And again, I think I also specified the homeworks on the information sheets that I had posted on Blackboard and emailed to everybody in the class. So yesterday or Monday, we looked at continuous functions, and in particular, the mean value theorem, which is one of the more useful theorems in calculus. And today, we look at infinite limits. But I think I want to do 1 or 2 problems on continuity just so we've seen some. So these are some homework problems in section 2.4. Exercise 39. So in exercise 39, we have the function f of x equals 6 over x. And the question for all of these exercises is find the values where the function is not continuous and which of the discontinuities are removable. So if you look at the graph of the function f of x equals 6 over x, it's a rectangular hyperbola. It's a hyperbola. It looks like this. And this is defined and makes sense everywhere except x equal to 0. So the only point where it's discontinuous at x equals 0. So I should say maybe it's continuous for all x different from 0. It's discontinuous at x equals 0. Now what happens if you take the limit, the one-sided limit, as x approaches 0 from the right? That's what the plus sign means. So as x goes to 0 from the right, this limit goes to infinity. On the other hand, if we take the one-sided limit as x goes to 0 from the left, this is minus infinity. And because the limit from the right is not equal to the limit from the left, even though they both exist, this implies x equals 0 is not a removable discontinuity. Discontinuity is removable if you could redefine the function at the point and get a continuous function. So x equals 0 is not a removable discontinuity. All right? So there are 3 words here that you have to understand, or 3 phrases, expressions. The notion of a one-sided limit, and there are 2 types, the limit from the right and the limit from the left. The plus sign means limit from the right, the minus sign means limit from the left, and the notion of a removable discontinuity. Any questions about that? Good. Let's look at problem 2. Sorry, page 2. Let's look at the next problem, number in that same section, number 41. So here we're looking at the function f of x equals 1 over 4 minus x squared. And you know you can factor the denominator into 2 minus x times 2 plus x. So this function is not defined at plus or minus 2. The denominator would be 0. So f of x is continuous at all x except plus or minus 2. And f of x is certainly discontinuous at x equal 2 and at x equal negative 2 because the function's not defined there. Suppose we take the right and left-handed limits. So let's consider x equal 2. The limit of f of x as x approaches 2, that's from the right, the limit as x approaches 2 from the right, 1 over 2 minus x, 2 plus x. Actually, I can make it a little bit easier. The limit as x approaches, well, no, I should have kept it like that, I'm sorry. The limit as x approaches 2 from the right of f of x, that's the limit as x approaches 2 from the right of 1 over 2 minus x times 2 plus x. What happens to that? Well, as x approaches 2 from either side, 2 plus x approaches 4. This means x is approaching 2 from the right, so x is bigger than 2, so this is negative. So this number is negative and going to 0 in the denominator. So this is going to minus infinity. And the limit as x approaches 2 from the right, from the left, sorry, this is from the right, this is from the left. Again, this approaches 2. Here x is less than 2, so this is a positive number going to 0. This is plus infinity. In any case, because the limit as x approaches 2 from the right or the left doesn't exist, the function's not continuous there. So x equal 2 is not a removable discontinuity. There's no way to redefine the function at x equal 2 to have a limit, and x equal
Professor, what's that
minus
word? I'm sorry, what's the word on your 4th line next to all the scribble?
Here?
Yes, that one.
Consider. Consider x equal to, well,
Plus or minus 2, thank you.
so first I'm looking at the case x equal 2, and x equal 2 is also not a removable discontinuity because again, the limit doesn't exist. Oops, I'm sorry. What I did was number 43, not 41. Let's look at number 47. So number 47, we have the function f of x equals x over x squared minus x. And this denominator, x squared minus x equals 0, if x equals 0 or x equal 1. So f of x is discontinuous So f of x is not defined at x equals 0 and x equal 1. So f of x is discontinuous at those points. Suppose we take the limit of f of x as x approaches 0, let's say from the right. So that's the limit as x approaches 0 of x over x squared minus x. But you can notice, observe, x squared minus x is x times x minus 1. So if you take x over x squared minus 1, that's x over x times x minus 1. That's 1 over x minus 1. So this is exactly the same as the limit as x goes to 0 of 1 over x minus 1. And that limit exists. That's minus 1. And in fact, that limit exists from the left and the right. This limit just simply exists. So see, what is the function? What is the graph of the function f of x equals x over x squared minus 1 look like? At 0 and at 1, it's not defined. If x is different from 0, the function looks like 1 over x minus 1. And so the graph of the function is that. And so the function's not defined at 0 and it's not defined at 1, but we can, if we define a new function, I'll call it f tilde of x, which is equal to x over x squared minus 1 for all x different from 0 and minus 1 when x equals 0, f tilde of x is continuous.
Can you move the paper up a little, please?
Oh, thank you.
Thank you.
So if we define a new function, I call it f tilde of x, f with a little squiggle over it. For x different from 0, it's x over x squared minus 1. And at x equals 0, we define it to be 1. Then this new function, f tilde of x, is continuous at x equals 0. So x equals 0 is a removable discontinuity. Right. So this function for x less than 1 looks like this with a little hole there. And you can basically fill in that hole. You can assign a new value to the function at 0, and you get this very nice continuous function. So that is the idea of a removable discontinuity. Any questions about this? So,
Hold on 1 minute. Ooh,
yep, go ahead.
I'm having trouble understanding how did you get the removable discontinuity?
Well, I'll draw another picture. We'll take another example. Suppose we have f of x equals x plus 3 over x squared minus 9. So, sorry, let me make it different. Make it easier. I'll make it x squared minus 9 over x minus 3. So this is defined wherever the denominator is not 0. That is for all x different from 3. So the function, so f of x is not defined at x equals 3. And if a function is not defined at a point, it's discontinuous there. So f of x is discontinuous. That means not continuous at x equals 3. All right. On the other hand, for x not equal to 3, x squared minus 9 over x minus 3, the numerator factors, x minus 3, x plus 3 over x minus 3. These cancel, you get x plus 3. So the limit as x goes to 3 of this function f of x is the same as the limit as x goes to 3 of x plus 3, which is equal to 6. What does the graph of f of x look like?
Can you move the page up? Thank you.
So this function's not defined at x equals 3, but everywhere else, it's a straight line. So this is the graph of the function. It just has a hole at this point, 3, 6. So the function isn't continuous at x equals 3 because it's not defined at x equals 3. But if we defined a new function, I'll call it f tilde of x, which is the same as f of x for x not equal to 3, and 6 when n equals 3, then the graph is this straight line. So f tilde of x is continuous at x equals 3. So by redefining the value of the function as 3, I get a new function which is continuous. So therefore, the language that we use to describe this phenomenon is x equals 3 is a removable discontinuity. Okay.
Thank you.
Okay. So now we go to the lesson of the day, which is section 2.5 on infinite limits. And we start out by looking at a function just like the kinds of functions we have been looking at, 3 over x minus 2. And this is only defined for x different from 2. What the graph of this function looks like is 0, 1, 2. When x is equal to 0, it takes the value minus 3/2. This is the graph of the function. Okay. And for this function, the limit as x approaches 2 from the right, that right-sided limit, function shooting up to infinity. The limit as x goes to 2 from the left, the function shooting down to minus infinity. And this is exactly what we mean by having limits at infinity as x approaches some particular number. Let's look at another example, maybe an easier. So here, as you approach 2 from the right, the limit is plus infinity. As you approach 2 from the left, the limit is minus infinity. Let's look at a second example. Suppose you have f of x equals 1 over x squared. The graph of that, symmetric around the x-axis. This is defined for x different from 0. And for this function, as x approaches 0 from the right or the left, f of x is shooting up to infinity. So these are examples of infinite limits. It means as you get closer and closer to some particular number c, the value of the function is either getting bigger and bigger and bigger, or smaller and smaller and smaller. And there's a very nice formal definition, which I will write down, but the whole concept is described by the picture that I drew. So we say, so this is a definition. We say for a function f of x, the limit of f of x as x approaches c is infinity if for every number m, no matter how big, every positive number m, there exists a number delta, that's a small lowercase Greek letter delta greater than 0, such that if x is within delta of c, so if x is less than c plus delta and greater than c minus delta, then f of x is greater than m. So if we had a graph that looks like this, this is my number c. If I take any number m, no matter how big, there's some little interval around c. So this would be c plus delta. That would be c minus delta. There'd be some little interval around c. And if x is in that interval, then the graph of the function lies above this line. F of x is greater than m. And there's a completely analogous definition of what it means for the limit to go to minus infinity, or for the one-sided limits. The limit as x goes to infinity as x goes to c from the right or the left, going to plus or minus infinity. And this is really all just an exercise in drawing pictures and interpreting them properly. So I'm just going to write down a few examples. Suppose we have, so these are examples. Suppose we have f of x equal to 1 over x minus 1 squared. So this is the vertical line, x equal 1. This is defined for x different from 0. Sorry, for x different from 1. When x equals 1, you would get a 0 in the denominator. This is also always positive, because the square of any number that's not 0 is strictly greater than 0. So this curve lies above the x-axis everywhere. And as you approach 1, it's going to infinity. So for this function, the limit as x goes to 1 is infinity. By the way, if you are using Maple in Math 155, or maybe you're using some other software, you still have to be able to use the software to graph functions. And if you just graph these functions in Maple, or in whatever software you're using, you'll get very clear, beautiful pictures of what's going on geometrically. So I urge you all to learn how to use your software in Math 155 to sketch functions. Here's another example. F of x equals -1 over x minus 1. Again, it's only defined for x different from 1. Now, if you look at this, if x is bigger than 1, the denominator is positive. So -1 over a positive is negative. This is the vertical line, x equal 1. So this function is negative for x greater than 1. And if you graph it, the graph looks like that. And if x is less than 1, x minus 1 is negative, and negative over negative is positive. So this function is positive for x less than 1. And as you approach x equal 1, this goes to infinity. So for this function, we say the limit of f of x as x goes to 1 from the right is plus infinity. And the limit of f of x as x goes from 1 to 1 from the left, sorry, this is minus infinity. As you approach 1 from the left, as you approach 1 from the right, the function is going to minus infinity. As you approach 1 from the left, you're going to plus infinity. So those are infinite one-sided limits.
How come we don't use the open circle for this if x doesn't equal 1?
I don't know what you mean, but you mean on the graph?
Yeah, the graph.
Well, where would you put the open circle? Because
Where the
there's
line?
no place, I mean, that doesn't make any sense in this context, because you see, if you had a function which looked like this example that we had before. Here we have a function which is a straight line, except it's missing, the function is not defined for x equal 3. But so this is missing on the graph. So I put a hole there to indicate it's missing. And the hole is there and not here because doesn't make any sense there. Here it's just like, it looks like there should be a number there. There should be a point on the graph, but it's not defined and it's missing. In these examples, it's not like there's some value you could plug in for x equal 1 and you would get some kind of continuous function. This is going to minus infinity. This is going to plus infinity. You can put a circle there, but it doesn't mean anything.
Okay.
So those circles only make sense when your function has a removable discontinuity, where you have equal right and left sided limits, but the function at a point, as you approach a point C, or at a point x equals C, but the function is not defined at C. And then you put the hole where that limit is. But here it just doesn't, there's no way to do it in any meaningful way. Now for this function, this vertical line, x equal 1, this is what is called a vertical asymptote. This means as x approaches 1, the graph gets closer and closer to this vertical line. And So if the limit of f of x for any function as x approaches c from the right or from the left equals plus infinity or minus infinity, then the line x equals c, this is a vertical line, is called a vertical asymptote. So you have a vertical asymptote wherever the function is approaching either plus or minus infinity from one side or the other. So these are important words in mathematics. And they actually have filtered into like normal conversations. People often talk about, well, it's not exactly that, but it's asymptotically that. And it just means it's getting closer and closer and closer. So there's a theorem that summarizes a lot of what we've just been saying about asymptotes, and that is in the text, what is labeled theorem 2.14. So if we have functions f of x and g of x, continuous functions on an open interval containing the point C, and if f of x, if f at C so the value of the function f evaluated at C is not 0, but the value of the function g evaluated at C is 0, then the graph of the function f of x divided by g of x has a vertical asymptote at x equals C. So that's exactly what we saw in this example. We have the function minus 1 over x minus 1. So we're interested at the point C equal to 1. The function in the numerator, minus 1, is not 0. It's equal to minus 1. The function in the denominator is 0 when x is equal to 1. And we have a vertical asymptote at x equal 1. So this is just sort of recapitulating everything that we've been saying. Let's look at some more examples. Suppose we have the function f of x equal 1 over 2 times x minus 1. So for all these functions I'm going to write down, the problem is find the vertical asymptotes. Well, this function is 0 at x equal 1 and nowhere else. So this has a vertical asymptote at x equal 1. As you approach 1 or around 1, the numerator is not 0, it's the constant function 1. The denominator is 0 at 1 and nowhere else at all. This is a vertical asymptote at x equal 1. Suppose we take the function f of x equal to x squared plus 1 over x squared minus 1. Let's look at that more closely. X squared plus 1 is never 0. It's always at least 1. The denominator factors into x plus 1 times x minus 1. So this denominator is 0 when x equals 1, and it's 0 when x equals minus 1. So this function has two vertical asymptotes. This has vertical asymptotes at the line x equal 1 and x equal minus 1. Let's see. We've actually tried to graph this function. When x is between minus 1 and plus 1, this denominator is negative. When x is equal to 0, this has the value minus 1. And as you approach plus or minus 1, this is going to minus infinity. The graph looks like that. And when x is bigger than 1, the graph of the function looks like that. Oops, let me draw it better. This looks like this. So we have these two vertical asymptotes. This is the line x equal 1. This is the line x equal minus 1. What about the function f of x equals cotangent of x? Well, what is the cotangent? The cotangent is cosine x over sine x. Sine of x equals 0 when x is a multiple of pi. What does the graph of this cotangent look like? So let's call this 0, pi, minus pi. Cotangent of pi over 2 is 0 over 1. As you go from 0 to pi over 2, or in the interval between 0 and pi over 2, the sine and the cosine are both positive. And as you approach 0 from the right, cosine approaches 1, sine is approaching 0. You're going to plus infinity. What happens as you approach 0 from the left? Well, when x is negative and approaching 0, the cosine is still positive, but the sine is negative. At minus pi over 2, the cosine is 0. And as you approach 0, this is approaching, oops, let's see.
Can you move the paper up a little, please?
Oh, sorry.
Thank you.
So when x is negative, the sign is negative, and the cosine is still positive for x close to 0. So this is a negative number, and this is approaching 1, and this is approaching 0 from the left. It's going to look like this. And in fact, the whole cotangent looks like this. So in fact, cotangent of x has vertical asymptotes at all multiples of pi, 0 plus or minus 1 plus or minus 2, and so forth. Right? Those are the vertical asymptotes of the cotangent. And for all three of these examples, they're nice pictures in the book. I mean, I drew pictures, but Maple will draw better pictures for you, and the textbook has better pictures. Now let's keep looking at examples. Suppose we have the following function. F of x equals x squared plus 2x minus 8 over x squared minus 4. Now, of course, x squared minus 4 factors. So this function is discontinuous at plus or minus 2, but that doesn't mean it has vertical asymptotes there. Because the numerator also factors. X squared plus 2x minus 8 is, I think, x plus 4 times x minus 2. So this numerator is x plus 4, x minus 2, and the denominator is x plus 2, x minus 2. These cancel. So for x different from 2, this is equal to x plus 4 over x plus 2. So this graph, f of x, has a vertical asymptote at x equal negative 2. Because at negative 2, the numerator is not 0, but the denominator is 0. And x equal plus 2 is not a vertical asymptote. X equal 2 is a removable discontinuity. Okay. Let me just keep doing examples because this is the kind of mathematics you did not see in pre-calculus probably. Suppose we have the function x squared minus 3x over x minus 1. We ask about the, now this is not defined at x equal 1, but we can ask about the limits from the right and the limits from the left of that function. Now, as x approaches 1 from the right, the numerator is going to 1 minus 3. It's negative. And this is positive, but going to 0. So this is going to minus infinity. If you approach 1 from the left, x is less than 1, so x minus 1 is negative. X squared minus 3x is negative. It's approaching negative 2. Negative over negative is positive. So this is plus infinity.
Can you do that one more time, please?
Sure. So here, this function, if we actually looked at the graph of this function, at x equal 1, it's not defined because the denominator would be 0. When x is equal to 0, you get 0. If you like, when x is equal to 2, what is x when x is equal to 2? 4 minus 6 is minus 2. And as x approaches 1 from the left, we have negative over negative. This is approaching plus infinity. As x approaches 1 from the right, this is going to minus infinity.
Sorry, I'm not sure about that.
When x is equal to 0, when x is equal to 3, you can see we get 0. The graph of the function looks something like this. So as you approach 1 from the right, the graph is going to minus infinity. As you approach 1 from the left, the graph is going to plus infinity. Those are the limits. So x equal 1 is a vertical asymptote, and you have different right and left-sided limits as you approach 1. Plus or minus infinity for both of them.
Thank you.
Okay. Let's see. I like to take attendance every now and then, so think about that for a minute while I just check off a kind of attendance. I have Saeed.
I'm here.
Reyes. No, I'm just reading the names that are on the on my computer screen. Thomas, Calderon, Augusto Garcia, Carlos German, Elijah Atkins, Eric Quayle, Gonzalez, Marlene Groulon, Nina Noble, Oscar Garcia, Rachel Scott, Raphael Groulon, Shakira Seymour, Zakira Khan. Zainab. Let's see. Okay, I think I got everybody.
Professor, I didn't hear my name.
What is your name?
Mohammed Osman.
Uh-huh. So what is your screen name? Because I don't have that name on my screen, but I do have an ENMI. Is that you? Oh, Mohammed Osman. Now I see you. Okay, you're there. Oh, and me Blanco. Fair enough. Gotcha. Okay, well, so that's everything in this section on infinite limits and asymptotes. And I'm going to spend a few minutes just doing some problems of the type that you will have on the homework. So in these problems, we want to find the vertical asymptotes. So we have the function, for example, 1 over x squared minus 9. If you factor the denominator, then you should be able to see pretty clearly that the denominator is 0 at 3 and negative 3. When x is equal to 0, the value of the function is minus 9. And when x is in between negative 3 and 3, this is negative. So we have a negative number going to 0. So the reciprocal is going to minus infinity. And when x is bigger than 3 or less than negative 3, this is positive. And the graph of the function is going to plus infinity. So we have vertical asymptotes at x equal 3 and x equal minus 3. All right, any questions about that? I'll just do one or two more. Suppose we have f of x equal to the function 1 over e to the x minus 1. So to find asymptotes, you have to know where the denominator is 0. So e to the x minus 1 is 0 if and only if e to the x equals 1. That's the graph of y equals e to the x. It's equal to 1 just when x is equal to 0. So this function has a vertical asymptote at x equals 0. Any questions about that? Suppose I want to know what is the limit as x approaches 3 from the left of the function x plus 3 over x squared plus x minus 6. Sorry, make this negative 3 as x approaches minus 3 from the left. Now you see the problem is if I put in negative 3, I get 9 minus 3 minus 6 is 0, and minus 3 plus, I get 0 over 0 if I plug in. So this function is not continuous in negative 3, but that discontinuity is removable because I can factor x squared plus x minus 6 into x plus 3 times x minus 2. So this is the same as x plus 3 over x plus 3 times x minus 2. And these cancel. This is the same as the limit of 1 over x minus 2. So as x approaches minus 3 from the left or the right, this is approaching 1 over minus 3 minus 2, or minus 1 over 5. Okay, well, so we have a long weekend, actually a very long weekend because, long weekend, or just a weekend. We have class again on Monday. Do as many of the homework problems as you can. And for any things for which you have a question, you can ask me first thing in class on Monday, and I'll be happy to do the problems. Any questions about any of these? Okay, if not, then we are done for the day. Bye.